Welcome to the shape of space. This lecture is on Markov chains concerning their definition and some examples. And I have a second lesson on the same topic where I'll get into a little bit more of the technical details. In the previous lesson, we studied non-negative matrices. In this lesson, we're going to study a particular type of non-negative matrix known as a Markov chain. A Markov chain has entries that are between 0 and 1, basically probabilities, and it's used to track or describe the transitions between the discrete states. So a Markov chain is a stochastic or random process describing a sequence of possible events in which the probability of each event depends only on the state attained in the previous event. So there's no long-term effect from previous states, just the last state affects the next state you're going to go into. A countably infinite sequence in which the process changes state at discrete steps defines a discrete time Markov chain. So that'll be the topic of this lesson. There's also continuous time Markov chains where you talk about the rate at which you're leaving one state to go to other states, but we're not going to discuss those here. So more formally, let x sub n for n equals 1, 2, 0, 1, 2, and so on, be a sequence of random variables with a finite or countable infinite state space. So these are the states of the Markov chain. The random variable x sub n represents the state of a random system at time n. A random process is called a Markov chain if this conditional probability holds true. And it's saying the probability at time n plus 1 of going into state n plus 1, given all the previous states, is equal to the probability of going into state n plus 1 at time n plus 1, just given the probability of the last state, which is the kind of in probability words what I set up here about the event only depending on the the next state only depending on the previous state. So that's what this is saying in a rather precise but slightly more complicated way. So in here I repeat myself again. In other words, given the past history of a process, the transition to the next step, next state, only depends on the present state. This is known as the Markov property. This references to a Wikipedia article, I believe. And I'll give you that link in the description to the video. I have a few examples on this slide in the next couple of slides about Markov chains. I took them from different papers and books, and I'll get more into the precise technical details in the next lecture, but I just wanted to expose you to a few examples. So if you don't understand everything here, that's okay. We'll kind of go over these concepts later on. So here we have a Markov chain. It's drawn out as a graph. And so the states are S1, S2, S3, S4, and S5. And then these lines are basically the transition probabilities. So if we look at state 1, it's saying there's a probability of P11 if you're in state 1 going back to it when you make the transition. And then there's probabilities of going from state 1 to state 2, state 1 to state 3, state 1 to state 4, and state 1 to state 5. Then you notice once you get into state 2, you can return to it or go to any of the other remaining states, 3, 4, or 5, but you can't go back to 1. And then it continues in that manner. Once you get to 3, you can return to it, but only go to 4 and 5. And then 4, you can return to 4 or go to state 5. And once you hit state 5, you're stuck in there. That's an absorbing state. You can only return back to it. You notice all the arrows lead to it, but you can't get out of it. And then you can take this picture here and you can put the probabilities of these transitions into a matrix. So this first row represents the probability of going from state 1 to itself, to state 2, state 3, state 4, state 5. So we're just pulling these off and putting them here. Then just let's do one more. If the second row is state 2, so you can't go back to state 1, that's why there's a 0 there. You can return to state 2 in the next transition, or you can go to 3, 4, or 5 with these probabilities, and so on. Then you see the last state here, you can only return to itself. Each row has to add up to 1. You have to go somewhere when you have, every time you have a transition, you have to either go back to yourself or to some other state. And so and this is generally true for Markov chains, each row has to add to 1. So that's what this is showing here. And I give a reference. I took this from a paper. Here's another example from a paper. We have 3 states in this case, A, B, and C. And you have the probability. These are now specific probabilities written on the states. So you can go from A, you can go back to A, or you can go to B or C with these probabilities. You notice they add up to 1, 0.1, 0.1, 0.8, so that's 1. C, you can go back to itself, or you can go to A or B, and then you have probabilities concerning state B. So this is a little bit different from the last example in that you can, the last example, everything kind of went in one direction. Here you can go back and forth between the different states. And here's the reference to where I got this. All right, I have one more. We have one more example. I took this from a math exchange question and answer. I have the link down here for it. And we're asked to analyze this directed graph. It's a Markov chain. And we're not given specific probabilities, but we're just given the whether or not one state can communicate, or whether you can move from one state to another. And we're asked to find what are called communication classes. These are groups of states that can communicate with each other. So they almost act like a single state. And then we're also asked to classify whether the states are recurrent or transient, and what the period is in the case of recurrent. And I know you haven't seen these terms yet unless you've studied Markov chains before. So this is my approach of giving you sort of a first look at this. And then on the second lesson on Markov chains, I'll go a little bit more in detail into this topic. So let's do the communication classes. There's 5 of them. I can draw them or circle them. So first there's A. A can only communicate with itself, and it's an absorbing state. You can't get out of A once you're in there. And then there's another group of 5 states, B, C, D, E, and F. You notice you can go from B to C, E to D, D to F, and back. So you can communicate amongst all these 5 states, and then you can leave through 3 different routes. But you can't get back into these 5 once you leave. Let's continue. Then G is another one. That's a transient state. Once you leave, you can't get back to that. Then H and I is another communication class. And then there's a 5th communication class here. J, K, and L. And we're asked to classify the states. So A is recurrent, was period 1. You have to cover each transition, you have to come back to it. B, C, D, E, and F have period 2, and that's a little bit complex as to why that's true. For example, B, how many steps can you return to B? Well, you can do 1, 2, 3, 4, but then you could also do 1, 2, 3, 4, 5, 6, or you can oscillate as many times as you want here. So it's basically 4, 6, 8, 10, 12. All those are possible for B. C is similar. F is the period is 2. So the period of this communication class is the GCD of the periods of these different states, and that would be 2. G is transient, and you can never come back, so there's no period. It's basically infinite. So that's why we have infinite here for the period. H and I is the period is 2, right? You leave and come back, leave and come back. And then J, K, and L, the period is 1. The reason for that is you have the GCD of different periods. For example, you can come back to from J in 2 steps this way here, or you can do 1, 2, 3 steps. And you have a similar analysis for these other ones. K, you can go 1, 2, 3, or you can do 1, 2, 3, 4, 5. So you basically have almost all the possible numbers going back between even and odd, and so the GCD there would just be 1. So again, this is just your first look at this. I'll get back to these communication classes and recurrent and transient states in the second lecture on this topic. We have a variation on the conditional statement I stated earlier concerning the Markov property. Stated here, it's a bit subtle, but it's an important point. If the probability that you're in at time n, you're in state I, and at time n plus 1, in other words, the next transition, you go to state j, and that only depends on this probability, but not on what time you're in. So it doesn't depend on n. In that case, the Markov chain is said to be time homogeneous. There's other Markov chains where the probability of going from I to j depends on what time you're in. So for maybe n equals 1, it's one probability. For n equals 10, the probability is different. That would not be time homogeneous. Then we have a few other points here that I've made earlier, but I'll repeat them here. Let S equal or be the states of a given Markov chain. So I0, I1, I2. This is known as the state space for a Markov chain. If a Markov chain is in a given state I, then the sum of the transition probabilities from I going to other states must add to 1. So we saw that in our examples where we had the matrices and we looked across, and I mentioned the probabilities need to sum to 1. 2 states in a Markov chain are said to communicate if they are reachable from one another bidirectionally by a sequence of transitions with positive probability. We saw that in some of the examples. This is an equivalence relation. I'll give you a link to this concept here, which yields a set of communication classes, and we saw that how these we had sets of states that could communicate with each other. There were groupings which we call communication classes. A Markov chain is said to be irreducible if there is one communication class. So in other words, you can get from any one state to any other state in a certain number of steps. We have a few more definitions. Consider a Markov chain X sub n with states given here and transition probabilities. The transition probabilities can be represented in a matrix. We saw that. And I also, as I mentioned a few times, if you sum across the row, that represents going from one state to any of the other states, and that has to equal to 1. If the number of states is n, then the above matrix would be n by n. So we know that. So each row represents a state that you're in at time n, and then each column represents the state you're going in the next transition. And we talked about whether or not this depends on n. If it depends on n, then it's not time homogeneous. If it doesn't depend on n, then it's time homogeneous. T, this matrix here, is known as the transition matrix for the Markov chain. Yeah, I've said that. Like I said, most of what's here. Yeah, as defined, each row is a discrete probability distribution. A matrix with all non-negative, and this is a general definition, goes beyond Markov chains. A matrix with all non-negative entries and whose rows sum to 1 is said to be row stochastic. So Markov chains are an example of a row stochastic matrix. On this slide and the next, I'm going to discuss some probabilities concerning transitions from one state to another. The first one I want to look at is here at the top. It is possible to compute the probabilities of going from one state to another in n steps. And it's this probability here. So P, I, J, n superscript is the ij element of t to the n. T was the transition matrix in going from one state to another. And you can prove that if you raise this to the n power, it gives you the probabilities of moving from one state to the other in n steps. That's something called the Chapman-Kolmogorov equations. I'm not going to prove them here, but I'll give you a reference in the information to this video if you're interested in the details. To be clear and more precise than what I just said here, so Pijn is the probability of going from state I at step k, that's the k here, and being in state j at step n plus k. Now we need to be careful because there's a hidden thing in this statement. This includes the possibility of earlier visits to state j. So it's just saying at step k you're in state I, and you can go into state j several times, but when you hit state k plus n, you must be in state j. And so it includes the probability of returning to state j between steps k and n, k plus n. This is different from the probability of the first visit to state j starting from state I. So that's a different computation. The probabilities in transition matrix T are conditioned on a given state. It is possible to compute the probability of being in a given state if there are n steps based on an initial probability distribution. I kind of alluded to this earlier when I mentioned the last example, the state G, which you can only leave it, and I was mentioning that the only way to get in that state would be to start from there, and that's what these initial probabilities are. So P sub j to the 0 superscript is the probability that a given Markov chain is initially in state j. So that's the two pieces of information you need for a Markov chain. Is one, the initial distribution, which state do you start in, and then the transition probabilities of going from one state to another. So we can write this out if you have, here I'm showing an infinite number of states, but it could just be finite. And it's just showing the initial probability of being in state 1, state 2, state 3, and so on. And then if we have this and we have the transition probabilities, these Pijn, the probability of being in state j at step n, given initial probability distribution P0, is represented by the notation P sub j n, and we can compute that using the law of total probability. So it's for each initial state, and then times the probability of going from that initial state to state j in n steps. And you just sum over all the different states. I showed infinity here, but there could just be 10 states or a finite number of states. I copied the equation from the end of the last slide. We can write this in matrix notation. The above formula is P0 times column j and t to n power, which is this thing here. This is true for each value of j, and thus we have this equation here in matrix form. If we let Pn just equal these for j equal 1, 2, 3, and so forth, and then you have your P0, which we defined on the last slide. Okay, so this equation and this are the same. It's just that these are vectors and this is a matrix. And as I mentioned before, this doesn't need to be infinite, but if it is infinite, then this is infinite, and the matrix is of infinite dimension in terms of rows and columns. If it's finite, for example, if this is 20 terms, then this would also be 20 terms in this vector, and then the matrix would be 20 by 20. And this P sub j n is also known as the absolute or unconditional probability of being in state j at step n, given the initial probability distribution P superscript 0. And then we have another similar equation to this. We can also derive Pn from Pn minus 1 from the law of total probabilities. So it's just saying that we're looking for the same thing here, but we're given that in step n minus 1 transitions, we're in state I, and then you just need to multiply that times the probability of going from I to the desired state J that we're looking for here. And in matrix form, that's just Pn, this row vector, equals Pn minus 1, which is another row vector with just n minus 1s in all these positions here, times t. The Bernoulli scheme is a very simple example of a Markov chain. Consider a sequence of independent trials, each with fixed probability p of occurring, being successful, and therefore probability q equal 1 minus p of not occurring. You can think of maybe flipping a coin. In that case, p and q would each be 0.5, but you might have a loaded coin where the probability of heads is, say, a little bit higher, and then p and q would not be the same. You can, make up other things that might fit this model, maybe shooting a basketball or shooting a free throw. Maybe there's a probability p of making it for a given player and q of not making it. We equate success with the number 1 and failure with the number 0. In this way, our state space is 0, 1. We didn't have to do that, but that's one option. This gives us a two-state model, time homogeneous Markov chain at time k. K is the number of the trial. And we can represent it with this transition matrix here. So this would be state 0. This second row would be state 1. Column 1 would be state 0, and column 2 would be state 1. So the way to read this would be if you just had a failure, then the probability of having another failure is q, and the probability of having a success on the next trial is p. If you had a success, the probability of having a failure is q on the next trial, and then probability of having another success is p. And that's kind of what I wrote out here. The rows of the transition matrix are identical because the trials are independent, making the state transitions independent of current state. Okay, you might want to draw the diagram, but it's pretty simple. I mean, you're just going to have two vertices, and you can go back and forth between them with these probabilities. The next example is a linear random walk between two barriers. So we have an entity, a person perhaps, starts at any of the points 0, 1, 2 up to S on a ruled line. So I've drawn you a picture of it here. So you have your entity starting somewhere, and then they go randomly at each step back or forth. And these are the particular rules. There's variations on this, but this is one version. If the entity reaches 0, so in other words, one end barrier, it remains there with probability A, so it'll just return back with probability A, or it moves to state 1 on the next step with probability 1 minus A. Then you have a similar thing if you reach this barrier here, you remain there with probability B, so on the next step you go back, and then you move to state S minus 1 with probability 1 minus B. And then for all the states in the middle, from 1 to S minus 1, you don't stay in the same state. You go either lower or higher. So here's the probabilities. The entity moves to a lower number state, so for example 10 back to 9 with probability Q, and to the next higher number with probability 1 minus Q, so for example 10 to 11. So we can draw a transition diagram for this, which I'll show you on the next slide. So here's the matrix representing the state of things concerning the random walk. You can look at the first row here. So this is when you're in state 0, and you can return to 0 with probability A, or leave it going to state 1 with probability 1 minus A. And then all these other states are similar. if you're in state 1, you can go back 1 with probability Q, or you can move up to state 2 with probability P, and then it just continues until you hit this other barrier where if you're in the state S, you go back to state S with probability B, or you start shifting back in the other direction with probability 1 minus B. Okay, so you might want to try drawing this. This is a little bit more complex, but it's pretty much a straight line with the stage 0 and S having a line going back to itself, and then the other states just having lines going either forward or backward. I have another example here, a Markov chain with an infinite state space. It's similar to the random walk in the sense that you have a boundary at 0, but there's no boundary on the other end. You can keep running theoretically forever without hitting another barrier. So let's take a look at the example. Consider a system that either moves to a higher state or goes back to state 0 after a transition. For example, this could model the operating system on a personal computer that is turned on each morning, where it could continue for another day or crash and go to state 0 and need to be rebooted. The system has a variable lifetime whose length, measured in discrete units, has probability distribution P sub I. So for example, P sub 1 is the probability it crashes in 1 time unit, P sub 2 is the probability it crashes after 2 time units, and so on. The transition probabilities from one state to the next, where the states are 0, 1, 2, and so on, is given by this. So this first row is state 0, state 1, state 2, and so on. This can go on, and theoretically it could go on indefinitely. You keep running and running longer and longer, but the probabilities, of course, become smaller and smaller that you would last forever. So you still need to represent it with still these dots here. So in other words, there's no boundary on the right compared to our random walk from the last example. So for example, the first row, probability you crashed and you're just starting again, and then you crash, you don't last that day, that would be, or that time unit's P1. And this is the probability you get to the next day. Then here's the probability in this row that you're in state 1, you've lasted 1 day, and then you crash. And this is the probability that you don't crash and you go on to a second day, and then that's just continues the same pattern here. So the probabilities look a little bit odd. We could have just used P2 here and 1 minus P2, but there's a reason for using these more complex probabilities. They still add to 1 if you go across the row. Clearly this adds to 1. If you look at this, they have the same denominator, and when you add the top, the P2s cancel and you get 1 minus P1, and the same deal here. So they still add the 1, but they take into account some other factors, which I'll mention on the next couple of slides. There's a subtle point here. This is state dependent. The transitions are clearly state dependent. Depending on what state you're in, you have certain probabilities of going to different states, and so it's state dependent, but it's not dependent on how long the process has been running. And we need to distinguish between the process and the number of times that you transition back to state 0. The process goes beyond any transition back to state 0. So for example, you could be running for 10 units, crash, run another 20 units and crash, and that's 30 time units. That is not reflected in these probabilities. So it's technically time homogeneous, and this is a classification we talked about earlier, but it's a subtle point that's easy to miss. So hopefully you catch that distinction between the process running longer than the individual crashes in between that may happen, and the probabilities do not depend on how long the process has been running. So the next few slides are a little bit more technical. You could skip them and just go to the last slide concerning the Polya urn problem. If you're not too familiar with probability, you may or may not want to do that. If you're more familiar with probability and conditional probabilities, I have some additional explanation for this it's mainly focused on these probabilities in this matrix. I think I've said most of what's on this slide, but maybe just repeat some things to reinforce the ideas. The probabilities P sub I in the given Markov chain from the last slide represent the probability mass function of the system's lifetime distribution, where the lifetime is a number of discrete units, days, steps, cycles. The system operates before returning to state zero, for example, crashing or rebooting in the particular example I gave. The interpretation of P sub I, which I've mentioned once, but we'll say it again, is the probability that the system's lifetime is exactly I time units. So I is 1, 2, 3, and so forth. Just writing it out here, P sub I is the probability, the lifetime equals I, where the lifetime is a number of steps. The system survives before transitioning back to state zero. In the context of the system, in the example of a computer that is turned on each morning, the lifetime could represent the number of days the computer operates successfully before it crashes and needs a reboot, i.e. return to state zero. So P1 is the probability the system crashes after one time unit. P2 is the probability it survives one time unit and crashes after exactly 2. Pi is the probability the system survives I minus 1 time units and crashes exactly at I time units. The probabilities are greater than or equal to 0. And the sum, as I mentioned, the sum of each, this is in general true for a probability distribution. The sum of all these P sub i's equals 1. Okay, let's continue. I have more explanation. Hopefully this is helpful. So let me make a first try at explaining the denominators here and why we didn't just use P2 and 1 minus P2 and P3 and 1 minus P3. So for the computer system, starting on each morning, state 0, P1 is the immediate crash probability. If it survives, moves to state 1, the crash probability from there is scaled by the remaining mass distribution. That's this, the 1 minus P. Reflecting updated odds given that it did not crash early. This avoids over or underestimating failure risk in later stages, making the model realistic for systems with non-memoryless lifetimes, unlike a simple geometric distribution which would have constant probabilities. So we keep normalizing what's remaining in the predicted lifetime based on the probability distribution. Notice here we're dividing by 1 minus P1 minus P2, and then the next one, of course, you would have 1 minus P1 minus P2 minus P3. So let me take another shot at this in the next slide, and then after that we'll move on to the final example. Okay, a little bit more on this these probabilities. The probability of crashing from state I, and we've seen this, I've just put it in a more compressed format, is P sub I plus 1 divided by 1 minus, and then the sum of the P sub i's up to from k equals 1 to I. And that's this thing here is the probability the lifetime will be greater than I, which is, this is known as the hazard rate, the conditional probability of failure at step I plus 1 given survival past state I. The probability of continuing is this, and again, we've seen this, but I've put it in a more compressed form. So it's the probability of lifetime is greater than I plus 1 divided by the probability of the lifetime is greater than I. The conditional, and this is the conditional survival probability. This conditional framing is crucial because in the Markov property, decisions depend only on the current state, not the full history. By normalizing with the survival probability, this probability here, the chain embeds the entire distribution P sub I into local transitions, ensuring that paths through the states reproduce the desired lifetime probabilities exactly. Okay, so that's it for this example. I have one more example in this lesson, and then the next lesson gets a little bit more into the theory of Markov chains, although I have examples there also. On this slide, I want to talk about George Polya's urn scheme. If you haven't heard of him, George Polya was a famous Hungarian mathematician who lived also in the United States for many years. And a number of awards, 3 different awards are actually named in his honor. He lived to the age of 97, and this particular example is attributed to him along with many, many other famous works of mathematics. So assume that we have A white and B black balls in an urn. Let A plus B equal capital N. At each transition, so in other words, each step in our Markov process, we remove a ball from the urn at random and take note of its color. Before the next ball, drawing the next ball, we replace the removed ball along with S more balls of the same color. So if we take out a white ball, we put it back and then we put in S more white balls. If we pick a black ball, we put it back and we put in S more black balls. That's a transition or a step. If the number of white balls selected in the first R drawings is I, we define the system to be in state I. Suppose we're in state I. Of course, I has to be less than or equal to R. After drawing number R, this implies R minus black balls have been drawn so far, right? They have to, on each of the R drawings, it has to be either white or black. So if you've drawn I white, then you must have drawn R minus I black balls, and then the number of white balls in the urn would be A, which is what you started with, plus I plus times S. So each time you draw a white ball, you add S more, I times S more. And it's similarly for the number of black balls, it would be B times R minus I times S. So at the next drawing, the transition to I plus 1 occurs with probability given here. So this is the total number of balls in the urn at that point, and this is the number of white balls. So this is the probability of picking another white ball, and the probability of going to state I, in other words, where you don't pick another white ball, or you equivalently you pick a black ball, stated differently. That would just be B, the number of black balls you started with, plus R minus IS. So this is the number of black balls. This is the total number. This is the probability of picking another black ball at that point. And that's, if you do the computation, that's 1 minus this, so which is what we wanted, right? We want the different rows in our Markov chain to add up to 1. So why did I do this? Well, so far we were looking at only time homogeneous Markov chains. This is not time homogeneous. You notice R is the number of trials. So these probabilities differ depending on how many trials you've had. And so it's not time homogeneous. It's classified as a non-homogeneous Markov chain. Okay, so that was the last slide and the last example in this lesson, but I have another lesson on Markov chains, and then I have a final lesson in this whole series related to my book on least squares, and then I'm going to publish my book with any changes I've made based on my picking up typos and errors and doing all these videos. And I'll make the electronic version of the book available, but you won't see that advertised until I actually finish all the videos.